Hello everyone, hope you all are well. So today we will discuss the chemical properties of haloarenes. Basically haloarenes, these are the haloarenes. These haloarenes are already electron rich species. So it will not prefer to undergo nucleophilic substitution reaction, because it is already electron rich. So it will not prefer to undergo nucleophilic substitution reaction. Now, there are certain groups which will make it electrophilic, then nucleophilic reactions will take place. How? When this nitro group we placed, if we talk about this is halogen, and we keep NO2 group here. This NO2 group is electron withdrawing group. Electron withdrawing group withdraws the electron. It will withdraws the electron from this benzene ring. What will happen? It withdraws electron from this carbon, and due to which it will take electrons from here, and this carbon will complete its deficiency from this carbon and ultimate from this carbon. Due to which these benzene rings become electron deficient to some extent as compared to normal benzene. Only then this nucleophile will attack on this benzene ring. Only then it will undergo nucleophilic substitution reaction. So this will nitro group make its electron deficient, and the nucleophilic attack will take place easily. There are some examples of nucleophilic substitution reaction. First one is Dawes process. For this, there is the haloarene. It will take place in NaOH, 623 Kelvin temperature and 300 atmosphere pressure. It leads to the formation of sodium phenoxide. Then on reaction with dilute HCl, it leads to the formation of phenol. This is the nucleophilic reaction here, because this O negative will attack on this carbon and this Cl will be removed. So it is a nucleophilic substitution reaction. Next is substitution by amino group. Amino group. If we take any haloarene, addition of ammonia in the presence of copper oxide, 475 Kelvin temperature, 60 atmosphere pressure on heat, it will lead to the formation of aniline. Here in place of Cl, NH2 group will be attached and HCl will be removed. So this is about the nucleophilic substitution reaction in haloarenes. Second chemical property of haloarenes is electrophilic substitution reaction. Most of the haloarenes will undergo electrophilic substitution reaction. As we already discussed during nucleophilic substitution reaction, that electrophile is electron deficient species. So we already know haloarenes are containing benzene ring. Benzene ring is electron rich, so it acts as a nucleophile and it can easily attack on electrophile, and it will undergo electrophilic substitution reaction. What will happen? This is chlorobenzene. It will easily attack. Its electrons will move here and this will attack on this. Then what will happen? In the first step, there is attack on electrophile. First step is the attack on electrophile. Then after attack, what will we get? There is the positive sign, and this bond will here, this bond will here, and electrophile will be attached here. After this, we have to remove this hydrogen to make it aromatic, because here it is aromatic ring which is more stable. Here the aromat is lost. So make it stable, we will lose this proton, minus H, loss of proton. With the help of any base, this will be removed and it will go here, and this double bond will go here. Then what we get? This and Cl, it which attached at ortho position. Similarly, it will be attached at para position also. Now, there is step is same. First is attack on electrophile. This will go here. This will go here. Now, what will happen? Here we draw resonating structures. Double bond Cl, here is positive charge. Here we get the negative charge. This negative charge will move here and it will be here. So next negative charge. Next negative charge. Double bond Cl, here is positive. And here will become negative charge. Now in this step, there is the attack on electrophile. This negative will attack on electrophile. Then what will happen? Here is the double bond, here is Cl positive, and here hydrogen and electrophile. So to make it aromatic again, next step is loss of proton. This proton will be lost and this bond will move here, this will move here, and this will move here. After this electrophile will be attached at para position and these bonds will get formed, and here you get the Cl. So in this way, you will get the ortho and para product. Out of these ortho and para product, para will be the major. This is due to the reason because there is the steric hindrance. There will be the steric hindrance due to the presence of any group at ortho position, but there is no steric hindrance. So it will be the major product in any reaction. Now after this, if we talk about that this electrophilic substitution reaction will undergo by the compounds at ortho and para directing. So the group present Cl here, this is ortho and para directing, because whenever the reaction takes place, this negative sign will be at ortho position or at para position. It will never come at meta position. So it will always form ortho and para product. Now consider another thing. If we add an electron withdrawing group at ortho or para position, its effect will be more pronounced here as compared to meta. See, this is haloarene. On this haloarene, if we add NO2 group, NO2 group is electron withdrawing group. It will withdraws number of electrons, large number of electrons when it present at ortho and para position. Because when we discuss about ortho and para, the negative sign during the electrophilic substitution reaction will come at ortho and para position. This is meta and next one is ortho, Cl and O2. Whenever we did the electrophilic substitution reaction, negative sign will become here and here. Never it will come on these positions. So the effect due to resonance, the effect of NO2 will be more pronounced. The electron withdrawing group effect is more pronounced at ortho and para position. It can withdraws more number of electrons from ortho and para position as compared to meta position. So it will be more pronounced at ortho and para. So we will get the ortho and para product as the major products. Now there are certain examples of electrophilic substitution reaction. Now we will discuss some examples of electrophilic substitution reaction. This is normal haloalkane. This is normal haloarene. On this, we will perform number of reactions. First one is bromine. In the presence of iron, it will lead to bromination. In bromination, what will be happen? You will get two products. This X will remain as such. Instead of X, we can take chlorine. And this bromine will be attached at ortho position, as well as this bromine will attach at para position. Para product is the major product. This reaction is bromination. Second one is CH3COCl. It will occur in the presence of AlCl3 or FeCl3. This reaction is called Friedel-Crafts acylation. This group is acyl group. So it is called Friedel-Crafts acylation. What will we get? At the ortho and para position, this group will be attached. CCl, here COCl, COCH3. This is acyl group, and similarly we get the para product COCH3. Now next one is CH3Cl. As it is acyl group, this is acetyl group. So it is called Friedel-Crafts acetylation. It also occurs in the presence of AlCl3 or FeCl3, and we get the product. Similarly, ortho and para product. Ortho product is this, and para product is this. Now fourth reaction. Fourth reaction is nitration. For nitration, we will take concentrated HNO3 nitric acid along with concentrated H2SO4 sulfuric acid. When these both give together in any reaction, then nitration will take place. Means NO2 group will be attached at ortho and para position. Remember, para will be the major product in all the reactions we did. Last reaction is sulfonation. In sulfonation, we will add H2SO4 concentrated and heat it. You will get ortho and para product. These are the certain examples of electrophilic substitution reactions. Now after this, we will discuss some more miscellaneous reactions related to these haloarenes. Third one is miscellaneous reactions of haloarene. Miscellaneous reactions of haloarenes. Now in this case, we will discuss certain reactions of haloarenes. If we react this haloarene with magnesium metal in the presence of dry THF or dry ether, it will lead to the formation of Grignard reagent as we did in haloalkane part. This is Grignard reagent. Next is this haloarene will react with lithium and it leads to formation of phenyl lithium. This is partial positive negative, this is partial positive. This is phenyl lithium. As we form the alkyl lithium, similarly it is phenyl lithium, and with one lithium there is this halogen. This halogen is chlorine. Now next example is this reaction is the name reaction. As we did Wood's reaction, similar this reaction, halogen plus 2Na plus. In Wood's reaction, we have considered these both R groups are alkyl. Here we take these both groups are aryl. Then this reaction is called Fittig reaction. And it will take place in the presence of dry ether. What will happen? It will lead to the formation of biphenyl by the removal of this NaX plus 2NaX. Next reaction. If we combine Wood's and Fittig reaction, how? In one side you will take aryl halide along with sodium. On the other side we will take alkyl halide. What will happen? Similarly 2NaX will be removed and other will be combined. On the phenyl ring CH3 will be attached along with the evolution of 2NaX. This reaction is called Wood's Fittig reaction. This reaction is Wood's Fittig reaction. Now you can take screenshot if you require. Now let's proceed further. Similarly as Wood's as well as Fittig reaction, similarly there is another reaction but the metal is different. For example, if we take haloarene along with 2 copper along with single copper, is in this case you will take haloarene idoarene. Here is idobenzene. What will happen? This CuI2 will be removed and it leads to the formation of biphenyl plus CuI2. This reaction is called Ullmann's reaction. Ullmann's reaction. Now last is, as we discussed, there is a formation of Grignard reagent when it reacts with magnesium in the presence of dry ether. But here the situation is different as there is a more than one substitution. Here chlorine is present, here fluorine and here bromine. Now out of these only one bond will break to lead to the formation of Grignard reagent. This bond will be break because as we move down the group, fluorine, chlorine, bromine and iodine, as we move down the group, size increases, bond length increases and bond strength will decrease. If this bond is weak, then it will be easily broken. So it leads to the formation of Grignard reagent MgBr. This chlorine and this fluorine will remain as such. Now after this there is another reaction, reduction reaction. It will take place at certain specific conditions. Reduction. What will happen if there is a halogen? It will take at specific conditions, or we can use very strong reagent, lithium aluminium hydride, nickel sodium alloy. You can use as a reagent. Then what will happen? This will give the hydrogen. So here the addition of hydrogen take place. So hydrogen will be attached here and it leads to the formation of benzene. That's all about the chemical reactions of haloarenes. That's all for today. Thank you and have a nice day. For more such videos, kindly like, share and subscribe.